talked a little bit about complex numbers, or the thing that gets us to complex numbers, imaginary numbers. We have this equation we want to solve, but we can't solve it with the real numbers. Hold on. Now, there are a few different ways to think about this. One way is to think about this is, well, we're kind of playing a game. And we can make up the rules, and we want to see if the rules make any sense. So the rule we make up is there's this number. It's not a real number. It's equal to the square root of -1. That way we have a solution to this equation. You just have to put aside your instinct that this doesn't make sense. In math, we're fine with that. We'll just go on and see if we can build something. And I think the litmus test is it useful? And I think I've talked a little bit about how I don't think we have any electrical engineers in here, EEs, but they use imaginary numbers, complex numbers all the time to solve problems with circuits. Circuits, alternating current circuits, voltages and resistances. And it turns out that these come in. Now, they're never part of the final answer. They always tend to disappear, the imaginary numbers. We never have to deal with some real variable that's an imaginary number, an imaginary voltage or something like that. We also, we find these when we're dealing with quantum mechanics. Quantum mechanics is part of physics. Anybody taking physics here? Oh, we have one physicist. Good. In your initial physics classes, you're going to learn Newtonian mechanics. You know, how to calculate trajectories of moving objects, orbits, so forth. But when you get down to the microscopic level, down to atoms and electrons, mechanics breaks down and things start to follow different rules. I'm not a physics teacher today, so I'm not going to go into it too deeply. But basically, quantum mechanics takes particles like an electron or a proton, and it models them with a function, which we often use psi for. And this is a complex function. The function actually directly doesn't tell you anything about the electron or the proton. You have to do something with the function. The term we use is we apply an operator. And the operators we apply always take this function and turn it into real numbers that tell us something about the electron and the proton. But in the meantime, we have to deal with complex numbers, imaginary numbers plus real numbers. So that's why we're learning about this. Now, again, it's perfectly okay to kind of treat this as a game. It's got some rules, just like algebra. You learn the rules, you follow the rules, and you solve the problems. So, all right, so we define, first we're going to define imaginary numbers formally. They are numbers x such that x equals a I, where a is a real number, member of the reals, and I is equal to square root of -1. So all our imaginary numbers have this property. There's some real number times the square root of -1. And then we define complex numbers. A box around these as a number a plus bi, where a and b are reals, and at this point we don't even have to say, we know that I is always going to be the square root of -1. I don't know why I feel compelled to say this, but if you were an electrical engineer, they for some reason use J, meaning square root of -1. All right, so now we want to know how to manipulate these numbers. How do we do the standard operations we're used to? Some of these are pretty straightforward. For example, if I wanted to add two complex numbers, let's just do an example. 5 plus 2i plus 6 plus 3i. Well, you already have the right strategy, because if you thought of this as an x, you'd know how to do it. You just combine like terms. So we're going to add 5 and 6, and we're going to add 2i and 3i. So this is 11. And again, you could think of this as, you could think of this as, I'm going to use the distributive property, 2 plus 3i, and I'm going to get 11 plus 5i. So adding is, should be pretty straightforward. If I'm subtracting, it's the same thing, except I have 5 minus 6 minus 1, 2 minus 3 is minus 1, and I just have minus 1 plus minus I. The other day I was thinking about this lecture. I was thinking about this thing here, negative I. Is that a negative number? Not really. It's just I, the square root of -1, with a minus sign in front of it, which just means times -1. We can call this a negative imaginary number. It's not, if you add a negative imaginary number to a positive imaginary number, we work with it the same way we work with real numbers. But it's not, doesn't clearly have that same meaning that we describe in negative numbers. Okay, that's adding imaginary numbers, complex numbers. And we want to multiply two complex numbers. So again, let's take a look at an example. Plus 2i times 6 plus 3i. And we're going to use the distributive property. We can just use FOIL. So let's go over FOIL. First, 5 times 6 is 30. The outer is 5 times 3i. It's 15i. The inner is 2 times 6i is 12i. And here's the part where you have to pay attention. 2i times 3i is 6i squared. Let's leave that for a second. 30 plus, 15 plus 12i is 7i. 6i squared. What's I squared? Just -1. Right? That's how we defined it. So this just becomes -6. 30 minus 6 is 24. 27. So this is mechanics. Again, if you think of I initially as x, just use FOIL. But then when you get to the squared, you have to remember that becomes negative. This is where I remind you something I don't know how many times I'm going to say it during this class. This is just one of the most important patterns you'll find in algebra. What does this have to do with what's going on here? Let's say I have something like 1 plus 2i. Say a complex number. I want to find a way to convert this just a real number. Well, I multiply it by 1 minus 2i. Using my pattern here, that tells me this is 1 squared minus 2i squared. Let's work that through. This is 1 minus 4i squared. I squared is minus 1, so this is really 1 plus 4, or 5. So multiplying, you have like, a plus bi. Multiplying it by a minus bi is really powerful. For one thing, you get rid of the imaginary part, you get a real number. For another, you know this is going to be a positive number. It's going to be a squared plus b squared. This is such an important idea that we give this a name. We call it the complex conjugate. Pretty easy idea. You take a complex number, you switch the sign on the imaginary part, you have the complex conjugate, you multiply them together, you get a real number. All right. We're going to see an application of that next. If we wanted to divide two complex numbers, well, long division isn't going to hack this. Long division isn't going to help us any here. Let's write this as 5 plus 3i over 2 plus I. Let's think about this. If only this were a real number, we know how to deal with fractions, right? This was like, say, 5, for example. We have 5 over 5, that's 1, 3/5 I. So, that would be useful. How are we going to get there? Well, the way we do that is we're going to multiply the denominator here by its complex conjugate. But as in all things in algebra, we don't want to change this. We have to multiply it by 1. Well, 2 minus I over 2 minus I is definitely 1. So we can do that. On the bottom, we're going to get a squared plus b squared. That's going to be 4 plus 1 or 5. top, well, we just learned how to multiply. We're going to use FOIL. It's going to be 10 plus 6 minus 5i. That's I. Minus 3i squared. That's 4. Or 14 plus I over 5. Except they did something wrong there. Did anyone catch my error? Oh, yeah, this is 3. Yeah. Now, this is perfectly good, but what if we wanted to see this in the usual format, the standard format of a complex number? We just have to break it up. This is just 13 over 5 plus I over 5, like 1/5 I. And here we have just a real number, and I. All right, just a side note here. If I ask you, what's the square root of 4? I'm not going to write it like this because, as I mentioned, this symbol means the positive square root of 4, which is, of course, 2. I just, square root of 4 could be 2, or of course it could be positive 2. Well, I'm sorry, negative 2. You can square either of these and get 4. When it comes to finding the square root of -1, well, we've defined something called I, where I squared equals -1. You might think from this there ought to be two such numbers that you can square and get -1. And in fact, if you take minus I and square minus I, that's -1 squared, is I squared. -1 squared is 1, I squared is -1. So the point is that there are two roots to -1. Call one of them I and one of them minus I. All right. Standing up here and moving a lot. It's supposed to be 86 degrees. Anybody have any? It was predicted to be 86 degrees. Anyone know actually how hot it is in here?
It is 90 degrees earlier. So
wow, yeah. So in order to prevent my falling over and having to call the campus police and the EMT, take a break here. It's just cold water. Okay. So, aside from everything else I've said, there's another, important value to complex numbers. We take a look at quadratics. Quadratic equation of ax squared plus 3x plus c equals 0. We know that occasionally the discriminant, these squared minus 4ac, occasionally less than 0. Since in the quadratic formula, have the square root of the discriminant, you're going to get an imaginary number, which means your roots could be complex. Take a simple example. X squared plus 4x plus 5 equals 0. Well, straightforward way to go about that is, of course, just to apply the quadratic formula. You get b squared plus or minus root b squared minus 4ac 2a. So our a is 1, our b is 4, and our c is 5. So negative 16 plus or minus square root of negative b, sorry, 4. 16 minus 4ac, that's 20 all over 2. So we're going to have negative 2 plus or minus square root of 4 over 2. Is that right? Yeah. So this is negative 2. Our rules for radicals are going to work, minus 4, sorry, are going to still work. This is going to be plus or minus the square root of minus 1. So this is negative 2 plus or minus 5. That is to say, if we wanted to factor this equation, we could factor it as x minus negative 2 plus 5, or x minus negative 2 minus 5. If you wish, you can sit there and apply this out. You will find you come back to the original equation. So one way to think of imaginary numbers is they kind of complete or provide the set of numbers for which polynomial equations can all be solved. It turns out that not just quadratics, cubics, quintics, any degree polynomial can be solved. Well, both can be solved. Has roots which are in the complex numbers. We can't always find them very easily, you know, numerically, but they're there. Okay, we're going to, complex numbers are going to come back and haunt us a little later in the class, but then we're done with them for right now. Are there any questions about complex numbers?
I don't really understand how the square root of negative 4 over 2 became square root of negative 1.
Square root of negative 4 over 2. That's what you're asking about?
Yeah.
Okay, well, I'm just going to do one step at a time. Does that look good? Look familiar?
Oh, okay. Yeah.
Okay?
Yeah. Thank you.
I'm just used to taking a shortcut myself, like I said. Square root of 8 over 2. I would just go 2 and put it under there, square it. Square root of 8 divided by 4. good to think it through, follow the, step by step. Especially if you're confused about something, it's always better to do that. You won't make some mistake. All right. Take a breather here for a second. I have to say, it's been a couple of years since I've taught this class. And the last time I taught it, it was Monday, Wednesday, Friday, so broken up into 3 hours over 3 days. But doing it this way, twice a week, it just feels like this material is just flying by. Now, fortunately, most of you, I hope, have seen imaginary complex numbers before. If you haven't, you have to work a little harder, or you don't remember them that well. Do the homework carefully. Still not good, come see me or go to the, I mentioned this, the math department provides Tuesday, Thursday, I think at 5 o'clock in the math office, math majors, care to tutor, assist, help you with your homework, help you understand concepts. Now, the next section, well, I should write down what we're going to do next. Next section we're going to look at is 1.8, inequalities. And I know from my own experience that certain parts of this are real easy, which everyone just like, of course, that's obvious. And then, for reasons I don't quite understand, I'm not saying I sympathize with it, it's hard to get a handle on why is this so? Why are these, why is an inequality that much more confusing than equality? But let's start off with some basic rules here. We have A less than B, and A plus C is less than B plus C. Seems pretty obvious, right? We have 5 less than 7. 5 plus 1 is going to be less than 7 plus 1, right? 6 is less than 8. Pretty straightforward. Of course, we're talking about A less than or equal to B, and A plus C is going to be less than or equal to B plus C. The equality, well, if you have equality here, you'll have equality here. And, if you reverse the direction of the inequality, greater than or equal to, you get the same thing here. And since C could be the number we're adding, could be a negative number, subtract C for both sides. We would change the inequality. So that's the easy part. Where things get a little more complicated when we're dealing with multiplication. A is less than B. C is greater than 0. AC is less than BC. With an inequality, we have no problem. You can always, if these were equal, you can always multiply each side by some number. And the equality remains. I have to give you some thought. If 1 is less than 2, C is 3, and 3 is less than 6. But what if we're dealing with negative numbers? Negative 1 is less than, it's not less than. Negative 2 is less than negative 1. Then we multiply by 3. Sure, negative 6 is less than negative 3. What if just one of them is negative? Negative 1 less than 2. Well, negative 3 is less than 6. So up and down the line, it kind of makes sense. What happens when A is less than B, C is less than 0? So we have 1 less than 2. It's just equal to negative 1. Well, let's multiply both sides. Negative 1, negative 2. What just happened? Inequality reverses. Whenever you multiply or divide, because dividing is just multiplying by the reciprocal, you're going to reverse the inequality. So if A is less than B and C is less than 0, then A is going to be greater than B. And that's going to apply to the weaker version. Right? These just happen to be equal. Well, we know already that the result is right. So maybe I should make a list here. And try and consolidate here. You just have to realize that equal is optional. C less than 0, A greater than B. Now, A is less than B. What happens to 1 over A and 1 over B? Take an example. 2 is less than 3, about 1/2 and 1/3. What happens? 1/2 is greater. So at least if these are both positive, that's what happens. What happens here? One of these is negative, but we didn't see this, right? Negative 1/2 is still less than 1/3. see, it's going to reverse again. Negative 1/2 is less than negative 1/3. And of course, well, I can't put an equal here because, no, but. So, how do we write this? I'm going to have to put an if in here. A and B are greater than 0. A and B are less than 0. 1 over A is now greater than 1 over B. Otherwise, oh, I don't want to write that. Otherwise it could be a bunch of things. In particular, if either A or B is 0, we can't do this. One of these is undefined. So I guess you could say, I'm not even going to write it. If one of them is negative, the sign doesn't reverse. Okay. One other important property of inequalities. A is less than or equal to B. What's going on with my right hand today? It's not listening to me. And B is less than or equal to C. And of course we have A less than or equal to C. This is the transitive property. Transitivity. Okay, so these are our basic rules for dealing with inequalities. Let's do some problems, example problems, and we're also going to do a little graphing. So, problem 3x is less than 9x plus 4. I want to solve this, and I want to sketch it. Well, fortunately, I can add or subtract something from either side without changing the inequality. So I'm going to subtract 9x from both sides. And I'm going to get negative 6x less than 4. And now I want to divide by minus 6. Well, multiply or divide by negative numbers. I'm going to switch the inequality. And get x is greater than negative 2/3. Smart thing to do when these problems get a little more complex is to test your answer. Let's see, let's just pick a number here, like 0. 0 is greater than negative 2/3. It's easy to test. So let's plug it in. Say 3 times 0, that's 0. It's less than 9 times 0, which is 0 plus 4. Is this true? I mean, it's a good, good kind of, good way to check your work. This is pretty simple, but when you do more complicated problems, you might want to try this, just to see if you made some simple mistake along the way. It's not just a game. It actually has to work out. All right, so how would we graph this? We draw a number line. 1, -1. And where's -2/3? It's about here. Since this is greater than, not greater than, or equal to, this is an open interval. Right? Or, if you like, x such that x is, well, greater than -2/3. All right. I guess I was thinking, how do you write this interval? It's open on this side. -2/3, and it goes to infinity. It is open. So we could write this interval just like that. I'm going to stop here. We're going to take a break. Have a drink if you wish, water. And we'll start off again in about 5. Inequalities. You're going to see problems that look like this. This is really two different problems. And this is kind of a combined inequality. But it's really two inequalities. And they're connected with an and, which means x's have to fulfill both of these. Now, it turns out that with a problem like this one, we can be efficient when we solve it. It's like if you had a equals b equals c, you can always add d. You can do this. It's really two different equations, right? And by transitivity, a third one. So we can do the same thing with an inequality. So let's take a look at that. First thing we want to do is to get to our x is to add 2 to both sides. So 4 plus 2 less than or equal to 3x plus or minus 2 is, right, gives us 3x. 13 plus 2. 6 is less than or equal to 3x less than or equal to 15. Now here again, you want to be careful. We're going to want to divide by 3. Since 3 is positive, these are going to remain in the same direction. If we were dividing by a negative number or multiplying by a negative number, they would both switch. But so x divided by 3 is x. 6 divided by 3 is 2. 15 divided by 3 is 5. And that kind of tells us the solution here. It's an interval closed on one side and open on the other. And if we were to graph it, here to indicate that it's open, and just kind of shading to show the part of the graph that this works. I think this may have come up. Some student may have asked me if you can do this. That's also a perfectly acceptable way to show the graph. Now again, when you're doing a problem like this, it's always a good idea to do a check. So let's pick some number here. Only pick 3. It's obviously in the solution set. Let's go back to the original equation. See if that works. 4 less than or equal to 3 times 3 minus 2 less than 13. 9 minus 2 is 7, which is square root between 4 and 13. So that's just a simple check. It's not 100%, but you could have made some small error here. Some values might be off, but certainly 7 works. Okay, so this is a kind of a compound inequality. I guess that's the end of the easy stuff. Now I have to look at something that, relatively speaking, more difficult. So we're going to drop it. There it is. What would we do with this? You could go pretty far with this doing kind of a yes and check. Like you could plug in 0. 0 less than or equal to minus 6, yeah. So solution sets could include 0. Because obviously solution set's a lot bigger than that. And you want to be accurate about this. So the way we go about this is the same way initially if this was an equality. We're going to bring everything over to one side. Add 6 to both sides. Have 0 over here. And then we're going to factor. So this is x. What is it? X minus 3 times x minus 2 are equal to 0. Now, let's think about this for a second. If this were an equality, where would it be equal? It'd be equal at 2 and 3. So let's at least have some place to start. So these are important. They're, for lack of a better name, I'll call them critical points. They're where this is going to be equal to 0. So we actually know these points will be in the solution set. What we don't know yet in this class, but I'm going to tell you, is that because this is a polynomial, its values they change smoothly. If we were to graph this, we have points 2 and 3, and we have some kind of parabola here. So on one side of one of these points, things are all going to be positive. On another side, they're going to be negative. And on another side, they're going to be positive. How do we know that that has to be? Well, these are the only 2 places where this graph can be equal to 0. You know this, right? We solved it. So anything else is going to change smoothly, and unless it goes through these points, it's not going to change sign. So we can break the question up as to where the solution set is into three regions. On this side of 2, between 2 and 3, and on this side of 3. So all we have to do is plug in some numbers and check. So let's plug in 1. So 1 minus 5 is negative 4. That's less than minus 6. Right? So that means from 2 to negative infinity is going to work. The same thing from 3 onwards. We'll try 4. That's 16 minus 20 is minus 4. Less than, wait a minute, I think I made a mistake here. Oh, that means probably people aren't watching me carefully enough. Try again. There's 2, there's 3. What about 1? 1 minus 5 is negative 4. Is negative 4 less than or equal to minus 6? I guess that's what makes these inequalities confusing, right? We're comparing negative numbers. Negative 4 is greater than minus 6. So this area here is, not what we're looking at. Same thing if I plug in 4, I again get 16 minus 20 is minus 4. Again, not. So this area is not included. So all I have left is something in between. Don't we hate using fractions? 2.5, that would be 5 halves. Let's see. I mean, when I'm trying to check, I hate using fractions. 5 halves squared minus 5 times 5 halves, less than or equal to minus 6. So 25 over 4 minus 50 over 4 or equal to minus 6 minus 25 over 4 minus 6. That seems to be about minus 6.25. Is that true? Negative 6.25 less than or equal to negative 6? Yes. So what that tells me is that it's this area here that we're interested in. And because it's in less than or equal to, I'm going to fill in the dots for right this way. X such that greater than or equal to 2, less than or equal to 3. However you want to represent that. Now, a good question is, do we always get this pattern where it's not part of the solution set, it is, it's not. Often it will be, but not always. So, for example, I might have a slightly more complicated function, not a quadratic, that could kind of look like this. It has zeros in 3 places. But you see here, we reach 0, but we don't change sign. Here we do, and again, here we reach 0, but we don't change sign. So the best way to do these is check a point for each of the regions that are divided by the zeros. This is really the most complicated thing you're going to do in inequalities. I might introduce an absolute value. Okay, any questions about inequalities? I guess I have one more problem. It's just that much more complicated to show you. Unfortunately, the case that for a lot of things we do in this class, just having a mechanical procedure is not always enough. You actually have to think about it. So let's look at x minus 1 squared, x minus 3 less than 0. This is a problem from the book. They very conveniently factored for you. So we already know that the critical points are going to be 0, 1, and 3. Well, we've got a bunch of regions here. 1, 2, 3, 4. And we're going to have to evaluate each one of these regions. So, in this case, it might be useful to make a little chart. Let's start down here, minus 1. So what do we get here? It's just minus 1, minus 1, minus 2 squared, that's 4. So we have minus 4. Minus 1, minus 3, that's minus 4. And minus 1, minus 3 plus 3, 2. Okay, so this is what? I have to write it down. Minus 1 minus 2 squared times 2 I'm sorry?
Wouldn't it be -4 instead of -3? Because they're subtracting -1 from -3. Or
Yeah, that's, I'm a little, I knew I was doing something wrong there. Thank you. Okay, so this is 4. This is 4. So that's 16. So we have 16 less than 0. Well, that's, I'm just going to write this as false. All right. About a half. Problems are like not work. 1/2 times 1 minus 1/2. I'm sorry, 1/2 minus 1 squared times 1/2 minus 3. Well, now actually we don't have to evaluate all of this. We can just say this is positive, this is squared, so it has to be positive, and this is negative. 1/2, I'm just going to say negative is less than 0. So this is true. So that tells us this region here is going to be included. Since this is a less than Again, these are open. We're going to want to check 2, check this region. So let's try that. That'll be a little easier. 2 times 1 squared. Oh, well, again, 2 minus 3, that's negative. So, negative 3. So this area is also part of this. And finally, we can just try out here, try 4. So 4 times 3 squared times 1, well, that's positive, right? This is false. So it doesn't include out here. Now, one curious thing here is 1. I'd say, like, everything between 0, 1, or everything between 1 and 3 are included, but not 1? Well, let's check. Here we get 0. Everything here is 0. 0 is not less than 0. So we do have an open interval here. So how could we write this? We could write this as the open interval 0 to 1, union the open interval 1 to 3. Or we could do it in set notation too. All right. That's my point. We have to be careful. The sign on the function will not always change at every 0. And in this case, it does. We're still not done. We're still not done with inequalities. So what about, we've been dealing with polynomials with inequalities, what about rational expressions? How are we going to deal with that? Well, if this was an equality, it would be pretty simple, right? We multiply through by 1 minus x, taking note of the fact that because 1 minus x at 1 is 0, it's undefined, we could just say x is not equal to 1. Here we have an additional burden. Remember, when you multiply something by something, if it's positive, this doesn't change. But if it's negative, it does change. So we really have 2 problems here. In both cases, we're going to multiply by 1 minus x. We're going to have 1 plus x greater than or equal to 1 minus x. But with the proviso that 1 minus x is greater than or equal to, well, it can't be equal to 0. It's got to be greater than 0. If 1 minus x is less than 0, then we have a different inequality, 1 plus x less than or equal to 1 minus x. I'm going to stop here for a second. I want you to think about this. We can't, when we're multiplying through by a variable, we have to be, in an inequality, we have to be concerned, is that variable expression positive or negative? Because that's going to determine whether the inequality sign is going to flip or not. So this is one way to kind of keep track of it. You have 2 separate problems. This is the case under this condition. This is the case under this condition. Think about that. Make sure you understand it before we go forward. And ask a question about it. All right, now, as it turns out, what we're going to do in both these cases is the same. So we can save a little time here. know, it seems they did this the wrong way, but I don't think I did. I'm going to follow this through, even though I think I'm doing it the wrong way. So I'm going to subtract x from 1 from both sides. Well, that's simple. X has to be equal to 0. The only x that can be greater than or equal to negative x is 0. Same thing would be here. Yeah, apparently that's not the right way to do it. What's wrong with what I did? Well, let's think of an example that proves I'm wrong. Let's say x is a half. So this is 3 halves over a half. That's 3 greater than or equal to 1. So there's something wrong here. I don't really know what I did wrong. Too bad. Well, guess I'm not too old to learn something new. You just haven't figured it out yet. We'll go through this the way the book wants us to do it. They want me to subtract 1 from both sides. Put this over a common denominator. Okay, what do we get here? Negative plus, we get 2x. 1 minus x greater than or equal to 0. This has critical points at 0 and 1. 1 it kind of goes off to infinity. So again, this really bothers me. Should be simple algebra. Anybody who can figure out what I did wrong doesn't need to do homework. All right. So let's look at this. 0 and 1. Let's look at the different regions. I'm less than 0, let's say negative 1. It's negative 2 over 1 minus negative 1. It's negative 2 greater than 0. No. So this region is out. Let's try 2. 4 over 1 minus 2 is negative 1. Negative 4 greater than 0. This region is out. So the only region left that's possible is in here, is in half. They tried that already. 2 times a half is 1. 1 minus a half is 1 half. Is 2. 2 is greater than 0. So knee-jerk reaction is, since it's greater than or equal to, say it's from here to here. But if we look a little closer, it can't be 1, can it? Because that would be undefined. So the correct region is from 1 to 0. All right. I'm going to have to go figure out what I did wrong with that problem. All right. we've done enough for today.